Welcome to section 3.7, Sinusoidal Functions as Mathematical Models. At the end of this section, we should be able to address these questions. What are the key pieces of information we need to construct a sinusoidal mathematical model? How do we use these pieces of information to construct a mathematical model? Let's look at an example. Here we have a water wheel. Suppose that the water wheel pictured rotates at 6 revolutions per minute. 2 seconds after you start a stopwatch, point P on the rim of the wheel is at its greatest height, 13 feet, above the surface of the water. The center of the water wheel is 6 feet above the surface. Our first task: sketch the graph of D as a function of t in seconds since you started the stopwatch. Okay, well, to do that, we're going to need a set of axes. So we'll start there. Then we'll start creating our image, or our graph. First of all, I'm going to draw a line through the center of our water wheel at 6 feet above the horizontal axis, right here. Then I'm going to draw a line at the upper bound, the highest point on our water wheel, which would be 6 feet plus our radius of 7 feet, or 13 feet, which would be right up here. And another line at our lower bound, or 1 foot below the horizontal axis, 6 minus 7. From there, we're going to begin to sketch the actual motion on our Ferris wheel. First thing we're going to do is mark when we're at the highest point, which is 2 seconds after we start the stopwatch. So right there we'll be at the highest point, 2 seconds. And then we need to figure out when we're going to be at the highest point again. Well, we know that we make 6 revolutions per minute. So that's 1 revolution in 1/6 of a minute, which would translate into 1 revolution in 10 seconds. So my next high value would be 10 seconds after my first high value, or right here. That would imply that our low value would be halfway between, or 5 seconds after my first high value. To connect these 3 points, we need a smooth curve. So we will connect them and then continue with the graph on the left and the right. And there we've sketched our sinusoid. We can label these points. This is 2. 10 seconds later would be 12. In between would be 7. Up here, 13, minus 1, and 6. Our next task: assuming that D is a sinusoidal function of t, write a particular equation. Well, to write a particular equation, we need 5 pieces of information. First, we have to choose whether we're going to use sine or cosine. Then we need our amplitude, our horizontal dilation factor, our horizontal translation, and our vertical translation, or the phase displacement and the sinusoidal axis, and our b value. First, let's choose a function. Well, if we read the question again, we'll see that 2 seconds after we start a stopwatch, point P on the rim of the wheel is at its greatest height. Since the information we're provided talks about a maximum, and the cosine function starts at a maximum, the cosine function would be particularly appropriate for our equation. So the first thing we're going to choose is the function to be cosine. Next, we need to deal with the vertical information. So let's start with the sinusoidal axis, which is the center of our water wheel. The center of our water wheel is 6 feet above the surface. So our sinusoidal axis, or C value, will be 6. The C value is the vertical translation. The vertical dilation would be the distance from our sinusoidal axis to our upper or lower bound. Since we are at the top of our Ferris wheel, 13 feet above the surface of the water, and our sinusoidal axis is 6, then our amplitude would be 13 minus 6, or 7. Our period, we determined earlier, was 10 seconds. Knowing our period, we can calculate our b value, because our b value is 2 pi over the period. Finally, our phase displacement is the location of our first maximum value on our graph, which we see in the question is 2 seconds after we start the stopwatch. So we've chosen cosine, and we have our a, b, c, and d values. So our equation should be 6 plus 7 cosine pi over 5 times the quantity t minus 2. Now that we have our equation, we can ask specific questions about the situation. For instance, how high above or below the water's surface will P be at time t equals 17.5 seconds? At that time, will it be going up or down? Well, the easiest way to answer this question is to use our calculator. So what I've done is I've put the equation that we came up with, 6 plus 7 cosine pi over 5 times t minus 2, or x minus 2 for our calculator, and I've graphed it in a window that includes that 17.5 seconds along the x-axis and allows us to go up to the top and bottom of our water wheel. So if we look at our graph, we see the motion of p across time. To find out where we are at 17.5 seconds, we would need to put 17.5 into the equation, which we can do right here on the graph screen by using the trace button. I can type in 17.5 after I hit the trace button and hit enter, and I can see that I am approximately negative 0.7 feet below the water line, and I'm just past the minimum on my graph. So the answer to my question is negative 0.7 feet, and I'm going up as I continue to go around the water wheel. Here's another question we can ask about this scenario. At what time t was point P first emerging from the water? So if we think about our graph, what we're really looking for is when we are moving upward on our graph through the t or x-axis. So I'm going to pull my calculator out again, and this time I'm looking for this value right here where the graph is going up through the horizontal axis. To find that point, I can go back into my calc menu and find the 0, option 2. To find that 0, I need to move first all the way to the left of that 0. And then for my right bound, I need to be to the right of that 0. And hit enter. And I find that I'm at that 0 at 7.8611866 seconds. Note that this problem could also be solved algebraically. I've laid out the steps here to show you how we could solve for the t value when our height is 0. So you might want to pause and work your way through the steps. You'll notice at the bottom that the second to last step is to split our equation into two options, the plus and the minus, and then determine which value is the appropriate value for this location here on our graph, where we are emerging from the water for the first time, or rising up through the horizontal axis. Our first value on the plus side is 6.1388, which refers to this point right here. Our first value on the minus side is negative 2.1388, which is over here. Neither one of those is the point we need, but we recognize that going from the negative 2.1388 one period further, and we arrive here at the value we're interested in. So negative 2.1388 plus 10 is the 7.8611 we arrived at with our calculator.